Uh, Today we will start talking about, so this week, so let me show you the slide. There you go, one slide. Life is critical. Okay. So what do we mean by this? So we talked about the laws of order, right? Laws of disorder and laws of order. Okay, do you remember? Now I will speculate, and many people did speculate, that life is between order and disorder. Okay, but how? So life is at that critical place. Life appears at that critical place because life needs order to sustain its processes, but life needs disorder to be adaptable to changes. Okay? So today we will look at what physicists mean when they talk about a critical system, a disorder, order, and the transition between them, phase transition. So I want to start with a method called Monte Carlo method. Have you heard of it? Yes. You have heard of it. You never tried it. Just heard, right? Okay. Have you heard of the casino, Monte Carlo?
I tried that one. That's what I was mentioning. Not the method, but the casino.
Yes. So the method takes its name from the casino, okay? Which is basically a place where you throw dice, right? Random number generator. So let's usually this simple problem is stated for understanding of Monte Carlo. So if I take random numbers between 0 and 1, okay, random numbers, and then if I count the ones that are inside the unit circle divided by the total number, what do you expect to get? Units. So pi times 1 over 2 squared divided by 1 squared. Pi over 4. Right? So let's actually do this. And if you throw enough dice, then let's call this set S1. The number of S1 divided by total number will converge to pi over 4, right? So you can actually take this 4 to the other side and get an approximation of pi as the run continues, right? So we will not do it smoothly, we will just, okay, how many numbers do you want to use? 1 million maybe? Let me quickly change the font. Okay, so random numbers, 2 rows of columns. This one is column, right? Okay, 2 columns of random numbers, right? So how do you find the ones that are inside a unit circle? We can do sum of R1 squared plus R2 squared, right? Smaller than 1. Do you agree? and divide it by n, multiply it with 4, we should get pi. Are you ready? I haven't tried it before. There you go. We get pi to some. Okay, if I do it 10 million times, I get a better pi. Not that better. But yes, there you go. Much better pi, right? Are you with me? Yes. So today we will talk about so what Monte Carlo did is you throw some dice, you look at the system, and you take an average over many trials, and you get some physical property. Okay, today we will look at a particular case called, I think it's called Ising model, not Ising. So Ising model models magnetization. Have you heard of magnetization? You know what a magnet is? Yes. Have you heard of Curie temperature? Yes? What is Curie temperature? Again, you have heard of it. Yes, exactly. So if we have a magnet, let's say this is T, okay, and this is magnetization. Sorry, magnetization. Like the total strength of the magnet. If you are at 0 temperature, okay, then all the tiny magnets are aligned. So atomic magnets are aligned. So you have maximum magnetization. And as you increase the temperature, those tiny magnets fluctuate, right? And when you reach at the Curie temperature, you lose all magnetization. So 0 magnet. So this is the phase transition. So you go from order to disorder. Okay, here magnets are aligned, so you have a net magnetization. Here they are disordered. Do you have any questions so far? No? So we talked about order laws, but we mainly focused on biological kind of order, like pattern formation or something. There is one law of order that sits right in front of us, which is energy minimization. Okay, so if you are at 0 temperature, things go to their minimum energy, right? And for example, atoms reach their minimum energy by making bonds with other atoms. And why do we have order? Because the atoms are very similar to each other, right? So their environment eventually becomes similar. That's why you form crystals, depending on the bonding of the atoms. Are you following my argument? So if you have carbon atoms, 10 to the 23 of them, each one interacting with the other one in the same fashion, so you expect to get something ordered because they are all the same, right? But if you increase the temperature, and if those bonds are not strong enough, like in silicon, you get an amorphous material. Do you have any questions so far? Okay. So what about magnets? This Ising model is very simple but very rich. So it describes, do you remember this? U equals to minus mu dot B. Do you remember from Physics 102? Magnetic moments get lower energy when they are aligned with magnetic field. Why are you smiling?
I got C plus from Physics 102.
Okay. So now we will look at the case when two magnets interact. In fact, we will even simplify it further, and we'll assume that these tiny magnets can either have up state or down state. Do you have any questions so far? So let's call these states S1 and S2 as a vector, okay? And the energy, the interaction energy between them, if I write it in this way, where J is positive, what kind of interaction do they have? Do they want to be aligned or not aligned? Do they want to stay opposite to each other or to stay in the same direction? So let's derive. So if both of them is 1, okay, like if both of them are aligned, what is the energy? Minus J, right? If they are opposite, 1 and minus 1, what is the energy? Plus J. Which one is lower energy? Minus J. So they want to be aligned. Okay? Do you have any questions so far? Did you miss anything so far? So when this is positive, you have a ferromagnetic interaction. Ferromagnet. Okay? When J is negative, what do you have? No. No. Antiferromagnetic. Thank you all. So you have antiferromagnetic state where all spins want to be opposite. All neighbors want to be opposite to each other. Did I draw it properly? No. So you will have something like this. Do you have any questions so far? Yes.
This might be unrelated, but how do you know if an object is antiferromagnetic, not something else, but antiferromagnetic?
Very good question. That's a very good question. So, in the calculation that I do, for example, if I am allowed to switch off the magnetic interaction, then I see that non-magnetic state has higher energy than antiferromagnetic state. Did you follow? So I can do calculations using density functional theory, for example, right? So I take a material, I do a non-magnetic calculation, I get an energy value E1. Then I do a magnetic calculation, magnetic interaction is on, okay? But I see zero magnetization at the end of the calculation. But I see that E2 is smaller than E1. But how about experiments, right? What would you see in experiments? I don't know. Okay. But did you get a gist of an answer here? Yes, I hope so.
Maybe you can understand from the time when we apply magnetic field.
Ah.
Observe the time. How much time does it take to switch from one bed?
That's a very good approach. So you can see the dynamics of the system with respect to applied magnetic field. You are not happy.
Like, would it be a delayed reaction
I
compared to, for example,
I think so. Like first of all, this one will not get magnetized at all, I guess. So this one, the non-magnetic material would not interact with magnetic field because its spins are all fulfilled their dream. They have all found their pairs.
what, with any external field, would it be at least slightly paramagnetic?
Well, we are at the edge of my knowledge, so let's. This is embarrassing, but I don't know. I don't have a good answer. So let's move on. So we will look at ferromagnetic case. Where you expect all spins to be aligned eventually at 0 Kelvin, right? So let's look at.
Can I interrupt you with a question? I'm sorry, can I ask you a question? I'm interrupting, but
Yeah, go.
about the alignment
Of course.
of the particles. So is it like something one-dimensional? Could they only be facing the same way, or vice versa? Or could there be some? I mean, like, are we defining the parameters like they are either facing the same direction, or that they are not, but not specific like this? Or could there some angles?
Okay.
So is it one-dimensional or not?
In our model, there are only two states, like on and off. Okay, but normally there are these things called magnons, like phonons, photons, electrons. They are magnons that corresponds to this kind of oscillation. Like, let's say they are all aligned, but you introduce just like in the atoms when they are at their equilibrium. If you what? Yes, precession. Yes, very good. So if you just disturb this atom, it will create a wave, right? And we call them phonons. Okay. In the similar fashion, if you have like perfectly aligned magnetic moments, and then you process one of them, and that interacts with the other, processes the other, and you create a wave that acts as a particle called magnon.
But for our case, we are just like taking a binary kind of.
Yes, yes, and this is again. I don't want to go into too much discussion, but have you heard of quantum mechanics? Yes. So there, weird things happen. Like if you are measuring a spin of an electron in a certain direction, you either get +1/2 or -1/2. Although they could have been, quantum mechanically, when you operate on something, it just goes to one of its eigenvalues. So it's not far away from the truth, this interaction. Thank you. So let's think of 4 spins, okay? Just 4 spins. So how much energy do we have here in total? Go ahead, don't be scared. -4J. Just 4 spins.
So you have like four pairs, right?
Yes, like this interaction, this, and this. We don't have this interaction. Okay. Do you have any questions so far? No. So let's look at another state where this is present. So what is the total energy here? Minus 2J. Very good. Right? So what about...
Should be zero. Well, I think it should be zero.
is it?
Minus 1, minus 1, plus 1, plus 1.
Plus J minus J plus J minus J.
0?
Yes.
I trust you. So minus, minus, plus, plus. You're right. So what about this one?
Minus J plus 4.
Plus 4J. Okay. So remember Boltzmann distribution? Do you remember it? E to the... this is the probability of a certain state, kBT. Do you remember this? So if you are at a certain temperature, let's say you are at a certain temperature, the probability of having this state is e to the minus 4j over kBt. I mean, if you want to find the probability, you need to sum all other probabilities, right? Plus, for example, this one is e to the 0 kBt and e to the 4j over kBt. Do you understand what I'm doing? So let's say this is the total probabilities. This is the probability of this one happening. So it's very small, right? Compared to others. This is more probable and this is the most probable. Actually, in fact, if you go to 0 temperature, this will be infinitely more probable than the others, so it will be the only possibility and it will go there. Did you follow so far the discussion? Yes? So what we are going to do is we are going to simulate any configuration of spins at a certain temperature. Okay? At a certain temperature. So how do we do this? How will we do this and how it will connect to Monte Carlo method? Well, there we have Nicolas Metropolis, okay, from Los Alamos. By the way, I want to point out Los Alamos guys. Okay, they built the A-bomb. That's a different story. But Los Alamos brought so many brilliant people, right? Let's just name them. Feynman, von Neumann, right? Metropolis, Fermi. Who else? Ulam, definitely. And many others, right? And Feigenbaum, by the way, Los Alamos. So and generally numerically interesting thing came out of there because that was the place where computers were used massively for the first time, I guess, right? To calculate the effect of the explosion. You agree? So let's just look at Metropolis's magnum opus, the greatest work of Metropolis. Where is it? Just if we type Nicolas Metropolis and maybe Metropolis Monte Carlo. It's not. No? I wanted to show you the citations. It's more than, it's around 7,000. But I will show you the paper. Never mind. So this is the paper. Equation of state calculation by fast computing machines. Like iPhones. Okay, so da 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 da. This is this the part where the sublime part? Yes. We then calculate the change in energy of the system delta E, which is caused by the move. If delta E is smaller than 0, if the move would bring the system to a lower state energy, we allow the move and put the particle in its new position. I will explain this, but let's read it first from the original. If delta E is bigger than 0, we allow the move with the probability of this one, e to the minus delta E kBt. So here, I will tell you something more from this. Let me find that word, those words. It will be worth it. Just let me find it. Okay, never mind. So I had some point here. Let me make that point, and everything will be clear, I promise you. Okay? So how would you calculate magnetization in this system? Let's say you put 4 spins into a temperature of some T, and you want to find the total magnetization. How would you calculate it?
So we are going to deposit these in a lake for each case.
Well, I'm talking about this simple system that has, so what you are going to do is, for all possibilities, you have the energies, right? And those energies will give you the probabilities. Do you agree? So what is this total magnetization in this system? 4, right? If it's 1 plus 1 plus 1, it's 4. So can I do the following? I integrate over all possible states the probability of being at that energy times the magnetization at that energy. Yes? Yes, it's the expectation of magnetization. Did you follow this? Yes? So what we did is we sampled the whole system, then we took the possibilities and we multiplied them to find the average. Metropolis Monte Carlo approaches it a different way. Okay, it samples with that probability, then it takes the average. So let me restate this. In this case, we take all possibilities, multiply them with their probabilities, then sum them up, right? Then average them out. In the Metropolis case, you already choose the systems with the relevant probabilities, and then you average them out. Maybe who can explain what I just told you? Yes, tell me.
So there are many samples that he can take.
Mm-hmm.
He samples all of the many atoms configurations, then he ensembles them.
Yes.
Sum them.
That's the bad version.
Yes.
Yes. So what is the good version?
So good version is they just take not all the probabilities, but
Yeah.
just take some of those.
Yes.
And at the end of the day, you will get all the probabilities. Like
You take you take the states according to their probability already. You sample them according to their probability. Then you take those samples and you take the average. If I could find that sentence, it's much better put in Metropolis's paper. Please go ahead and read it and find that sentence. So let me restate it one final time. Instead of taking all possible states and averaging them according to their probabilities, we take the states according to their probabilities and average them out.
The number of states you are taking in the first case
Is
number of states I take in the second case, are they the same?
no.
That's
That's the whole point. The number in the first case, I have to take all numbers, everything that is possible.
You pick what is the sample size? Like, you take the highest, I don't know.
Let me tell you what I take. So Metropolis algorithm tells you that you should take them in the following way. So let's say you pick one single spin and you calculate what happens if you flip it. Okay? That's how you calculate delta E. So let's say you are here and I choose this one. What is the change in the energy if I flip it? Be careful when you calculate this.
It goes from minus 4j to reverse it
Yes?
to 4j.
So
So it's 8j.
8J. Do you agree? Yes? So Metropolis says that we should accept this flip with this probability, minus 8J over KBT. Okay? And what if you have something like this? Something like this. What if you flip this one? What is the delta E? Minus 8J. Everybody agrees? It's 4J before, then it's minus 4J. Did you follow? And according to Metropolis algorithm, if the energy decreases, you accept it. Okay? So by doing this, energy decreases, accept, energy increases, accept with this probability. If you continue doing this, then you are sampling according to Boltzmann distribution eventually. Okay? I was expecting that this part will take like 10 minutes, but it took 30. So I will not explain many details of this code. I hope you can figure it out. So, by the way, the only possible, by the flips, the only possible energy changes are minus 8J, minus 4J, 0, plus 4J, and plus 8J. So if the energy change is minus 8J, then there is one probability of switching. If it's minus 4J, one probability. What if the energy change is 0? Again, one probability because e to the 0 over kBt, right? But the others will switch with this probability. Okay? Did you follow all this? So I will start with random spins, up and downs. And this part, you can see that this is the flip the spin. That's all. And just these parts are making sure that you are choosing a random spin and according to the probability you flip it. Did you follow? So let's run it and see what we get. We get this interesting structure. I have to point out here that this is not the real dynamics. Okay, this is not like molecular dynamics. It's just we are sampling the system. Are you following? Do you agree?
Then how large is the matrix of the elements?
200 by 200.
So we take each, so in one sample, do
Yes.
take one?
No, that's a very good point. So each time this picture changes, we actually flip 200 squared spins.
All of them are
Not at the same time. That's very good. All of those are very good points, but I have very short time, unfortunately. Can you give me 5 more minutes after 10:30? Yes? So you are flipping each spin you are each time looking at one spin, and here I actually do that n squared times, but not necessarily with the same order.
So randomly you just pick.
Randomly I pick n squared times, I pick one spin, should I flip it or not? With certain probability I flip it or not. Did you follow all this?
Yeah, there are n squared choices you have, right? For each of that.
Sometimes one spin doesn't get picked at this n squared runs, but that's okay.
Yeah.
So let's see. So right now KBT is 2. What if I change temperature? So let's go to this code. So here I will start with 1.5. T minimum is 1.5. I will go to maximum temperature of 3. Then I will go back to 1.5. Then I will go back to 3. So I want you to see what happens when the temperature is changed. Okay? Ready? So this is low temperature, which means that you have aligned magnets. Do you agree? The blue parts are minus spins, so they are all aligned. You have big magnetization. Now we are approaching this critical temperature where you have transition from order. This is order, and you are going towards disorder. Okay? Where your magnetization will go down to 0. So you can see that we have almost equal amount of plus ones and minus ones. Are you following all this? Now, did we reach the maximum temperature? We have reached it now. Now we go back. So what will happen when we go back? Any ideas? Hmm? Yes. Once you go below critical temperature, you should see the order reappear. Right? Domains, very good. So you will see domains appear, and those domains, one of them will dominate. We don't know which one. So I think right now my bet is on yellow one. Right? One of them will dominate and flip the others. No? Blue one? So I'm taking the bets. Blue, yellow, okay. No one else betting?
Once you demagnetize something using temperature, you cool it so it becomes magnetic.
Yes.
So that's what happens.
Yes.
There's no hysteresis.
Yes, I was going to that.
What?
There is hysteresis.
Yes, there is a hysteresis, and again, let me restate. This is not an actual simulation of a magnet. We are just sampling the system. Are you confused? No? So this Ising model is not easy to solve at all. Okay? Although the name suggests that way. So it was solved by this genius, Lars Onsager. Have you heard of him? Not many people have heard of him. Yes, critical systems and far from equilibrium systems, right? He got the Nobel Prize in 1968 for this stuff. And he actually solved the Ising model uh, analytically. Can you believe it? Genius. So let's look at that paper. Two-dimensional model with an order-disorder transition. Let's just skip through this paper and you will see like different mathematics introduced to solve this quaternion algebra. So 33 pages of pure beauty. Do you see it?
So you did this alone?
Well, there's only his name here. But let's go to acknowledgements, which is before this long appendix. Is this still the appendix? No acknowledgement. Yes, what is the year? 1943. Right in the middle of the war, he solved this problem. So he gave us a very nice formula. Okay, let's find that formula for critical temperature, where the critical temperature occurs. Let's go ahead and find that formula. Yes, there it is. So if you rearrange it, KTC over J should be this weird number 2 over ln 1 plus square root 2. Okay? And we also have the formula for magnetization. Where is that formula? So we have analytical solution. Never mind. I have this formula in my code. Let me show you. This is that formula. 1 minus sine hyperbolic 2 times j over kbt to the power of minus 4 in the brackets to the power of 1 over 8. Never mind. So what I will do here, are you following? Yes? What I will do here is I will go from, so I will define Tc to be this number, 2 over logarithm 1 plus something. And I will go from half of the critical temperature to the 1.5 of the critical temperature. Okay? And each time we will start, we will do how many runs? Let's see. We will do 1,000 different runs. Okay? Each one flipping the spins 200 square times. So 200 square times 1,000 gives you 40 million, right? So we will sample 40 million pictures from the system. Do you agree? Well, let's run this code. And while it runs, I will talk about it. So we have run the first one of this temperature. So let me. What we are doing is, this one is T critical. So we start from 0.5 T critical. and we take the system, we run the system 1,000 times, and each time we flip 200 squared spins. But we only take the last 100 steps and average the magnetization from those pictures. Did you follow? Yes? What do we expect to get? So magnetization versus temperature. What would you expect? Let's say all spins pointing at the same direction is 1. So when the temperature is low, it should be very close to 1, right? Then at this point, it has to go sharply to 0, right? And remain at 0 forever, right? Let's see the result. There you go. And what is this line? The red line? Yes, analytical solution of Metropolis. Do you see that our numerical calculation using Metropolis algorithm is matching it almost perfectly? Do you have any questions? So this particular point where it switches will be critical for life. So this is where life wants to be, at the criticality. And at least now you have a sense of order and disorder. Next time we will explore those concepts even further. Do you have any questions? No? Thank you all. Take care.